Previously, given two smooth vector fields x and y, we have defined the notion of the Lie derivative of y in the direction of x at a point P. Remember what we did was we took an integral curve of x, so a curve so that whose tangent vector field is just the vector field x restricted to the curve. So a curve that is tangent to x at every point on the curve. And then at every time t, we look at the y gamma t, we push it forward along this curve, right? So that it lies inside the same tangent space as yp, and we look at the difference. We look at this difference, and we take the limit as time t goes to 0, the limit of this difference, and then that gives us the derivative of this vector field y along x. And then we claim that this limit turns out to just be the Lie bracket. So what is this Lie bracket? That's going to be the topic of discussion of this video. Now, what we want to do is we want to put some kind of algebraic structure on the set of smooth vector fields of M. In particular, we might want to define some kind of multiplication of vector fields. But the setting is if x is a vector field and y is a vector field, xy is not necessarily a vector field. What do we mean? What we mean is if x is a derivation, right, at the point P, and y is a derivation, xy is not necessarily a derivation. So to see that, let's first explain what the definition of xy is. Recall that every smooth vector field can also be viewed as the function on the smooth functions on M. So remember the definition was that x would send f to the functions that sends every point P to xp of f. Right, so this function, we call it xf. It's the function that sends every point P to xp of f. That's a smooth function. So now I will try to define this as a function also. So we define this to be x of yf, right? So yf is a function, and then so yf is a smooth function, and then x of yf is again a smooth function. So xy is a well-defined map from smooth function on M to smooth function on M. However, it's not going to be a derivation, so let's see why. Okay, so let's take xy of a product. By definition, that's just x of y of this. Now, because y is a derivation, we have this identity, and then by linearity of x, we can split this out. Now again, we use the fact that x is a derivation to split this. Now, if xy is a derivation, then we should only have these two terms, right? We shouldn't have these two extra terms. So let me rewrite it up here. If this was supposed to be a derivation, if xy is a derivation, then we should only have these terms. So then we see that xy is not a derivation, but we can try to fix this. By symmetry, if we replace x with y, if we switch x and y, we should have the following expression, just switching all of the y with all of the x. Now, let's subtract one expression from the other. Here, observe that this is equal to this, and this is equal to this. So all of those redundant terms cancel, and here we just have this identity, which shows that xy minus yx is actually a derivation. So we call this the Lie bracket of x and y. It turns out that if x and y are smooth, then this Lie bracket is also smooth. So the set of smooth vector fields on M is actually closed under this binary operation. The set of smooth vector fields on M under this Lie bracket operation form an algebraic structure called Lie algebra. Now, unlike what its name might suggest, a Lie algebra is actually not an algebra. Not quite, it is its own kind of thing. So, a Lie algebra over a field K, right, is, what is it? It's a vector space together with a product operation, a bilinear operation, that is anti-commutative and satisfy this Jacobi identity. So this sum of cyclic rotation of this xyz is equal to 0. So unlike usual algebra, we have this instead of usual associativity. Now our natural operation now would be, can we view this smooth vector field operation as a functor to the category of Lie algebra? More simply, we'll ask a simpler question. If we have a map between manifolds, does that induce a maps on vector fields? Can we push forward vector fields? The answer is gonna be no, but we can fix it, and that's gonna be discussed in the next video.